Good morning. This is the last part of Unit 5. Now, first of all, we should be habitual of the basic terminology which will be used. Primary cell. These are the cell which will serve as a source of energy as long as the active chemical species are present in the cell. These are irreversible cell. They are designed for only single discharge and they cannot be charged again. About the secondary cell, these cells are chargeable. They can be used again and again. The cell reactions are reversible. Now, concentration cell. It is the electrochemical cell consisting of the same metal electrode dipped in the same metal electrolyte solution but without different concentration, which we will see that in 6th unit. We know the process of oxidation, the process of reduction. Single electrode potential is the potential developed at the interface between metal and the solution when it is dipped in the solution of its own ion. Standard reduction potential, potential developed at the interface of the solution when it is dipped in the solution of its own ion at 1 molar concentration at 298 Kelvin. Standard condition. EMF, it is the potential difference between the two electrodes developed, which causes the flow of current from higher reduction potential to the electrode with lower reduction potential. Now EMF is equal to E right minus E left, or we call it as E cathode minus E anode. So depending on this standard reduction potential, if they are put in one order, we form a series known as electrochemical series. In this, there is the arrangement of elements in the increasing order of their reduction potential. So arrangement is like this. A positive value indicates reduction tendency with respect to the hydrogen. Metal with lower electrode potential is more reactive. As the electrode potential increases, the reactivity decreases. With higher electrode potential, noble. Metals with lower electrode potential have tendency to replace metals with higher electrode potential. Metal with negative electrode potential, they can liberate hydrogen. So like this, we can find out the electrochemical series. And it can be applied from that E0 of the cell, we can find out the spontaneity of the redox reaction. Suppose E0 of the cell is 0, then we can consider that the reaction is at equilibrium. If it is positive, we can consider that reaction as a spontaneous reaction. But if it is negative, we can consider it as a non-spontaneous reaction. If this value is more and more positive, that means stronger oxidizing agent, or it is more likely to be reduced. So next is Kohlrausch law. We have already seen that for strong electrolyte and a weak electrolyte, equivalent conductance increases with dilution. But there is a difference in the graph. For strong electrolyte, the graph is like this straight line, which we can extrapolate to find out the lambda infinity values, equivalent conductance at infinite dilution. But for weak electrolyte, the nature of the graph is like this. Like this. We don't know where to intercept. It can intercept here, here, or we can go ahead also. So we don't know the exact value of the lambda infinity for weak electrolyte. So for this situation, Kohlrausch law is there. At infinite dilution, the dissociation is complete, supposed to be complete. So each ion make definite contribution towards the equivalent conductance irrespective of the nature. So we have taken it as a cation plus anion. For example, NaCl, Na positive and Cl negative ions. Suppose we are dealing with the acetic acid, weak electrolyte, acetic acid, CH3COH. We don't know the lambda infinity value for the weak electrolyte. So what we have to do? We have to check the lambda infinity for CH3CO negative and H positive. Now this CH3CO negative can be combined to form strong electrolyte CH3CONa H can be combined to form strong electrolyte HCl. So CH3COOH plus HCl. And the extra NaCl can be subtracted to give the lambda infinity for weak electrolyte. Or another way is from the transport number. That means Kohlrausch law is useful for calculating the lambda infinity for weak electrolyte, useful for finding out the transport number also. If the numerical has been given, you should be able to calculate these values. Calculation of the absolute ionic mobilities. Ionic mobilities we can calculate, just we have seen. Then the sparingly soluble salt. Solubility of sparingly soluble salt. It can be also calculated. Sparingly soluble salt. Degree of dissociation alpha, which is nothing but the ratio of equivalent conductance to the equivalent conductance at infinite dilution. It can also be successfully calculated, and ionic mobility we have seen that. Now come to the Ostwald dilution law. Ostwald dilution law. We know this law already. Weak electrolyte, they ionize to a very small extent, and their molar conductivity, that does not attain the limiting value. So there is an equilibrium between free ions and the undissociated molecule. We can take 1, 0, 0. Then at equilibrium, degree of dissociation is alpha. So 1 minus alpha, alpha, alpha. Concentration is this. So K will be equal to product of this divided by this, which finally reduces to alpha square C 1 minus alpha. This is Ostwald dilution law. Now how the law is verified? This alpha, it is determined. This alpha is determined, and conductivity measurement has been seen. We divide it by certain dilution. The lambda V and lambda infinity we can find out. Now, what is the application? It is used in the dissociation constant of monobasic acid. Now, we will see the different applications of the conductivity measurements. Now, conductivity measurements, it has very important applications in different fields. Suppose we want to find out the degree of dissociation. Just like just previously in the Kohlrausch law, we have studied this. In the Ostwald dilution law also we have seen this. So this degree of dissociation, we can find out degree of dissociation using the conductivity measurements. We can find out the solubility product of the sparingly soluble salt by using this formula, where S is the solubility in moles per liter. This is the specific conductance of the saturated solution and the molar conductance at infinity. This method for determination of solubility product, it can be explained by taking the example of AgCl in water. AgCl, it is first washed with the conductivity water to remove any insoluble impurity, and after that it is suspended in conductivity water, warm and cooled. A very minute quantity of the salt will pass in the solution and the rest will settle down. The conductance of the solution and the water is used to find out the conductivity at 25 degrees Celsius. And by using the formula, we can find out the solubility. And the important application is in the conductometric titrations. The determination of endpoint of a titration, conductometric titration, by means of conductance measurement. In this titration, actual specific conductance of the solution is not required, and any quantity which is proportional to it is sufficient. The titrant is added from the burette, and the change in conductance, it is a function of added titrant, which is used to determine the equivalence point. A conductance cell in which a solution is to be titrated consists of the two electrodes with large surface area naturally. Typical example and the curves are like this. Now in all the titration, the area or the point of intersection of the two lines will be the equivalence point. Now we will see different cases. Suppose acid-base titration. In acid-base titration, we are titrating strong acid with strong base. Strong acid with strong base. This is a reaction. In normal course, we titrate HCl and NaOH using phenolphthalein indicator many times. Now here in conductometric titration, there is no need of addition of phenolphthalein indicator because phenolphthalein is added just to observe the color change at the endpoint. Here there is no need to observe the color change because the endpoint is determined graphically by the measurement of conductance. So no need to check the color change. That's why we don't have to add phenolphthalein in any conductometric or likewise potentiometric titrations. Here we are going to check the endpoint by the change in the conductance, and that is also graphically. So don't add any indicator. Just take HCl in a beaker, add NaOH from the burette. What will happen? This H positive, concentration of H positive ion decreases as it has been neutralized. One step will reach when all the solution is neutral. H positive vanishes, and now after more addition, the concentration or the OH negative ion, they are increasing, and that's why conductance again increases. So this is the nature of the graph, and the point of intersection of the two curves, two graph, two straight line will be the equivalence point. So this is for acid base, strong acid and strong base. This we can implement for any. Suppose there is a strong acid and weak base, we will always remember strong acid always gives such line. Weak base like this, slope. Slope will give the idea about the strength. Like this, strong base this, weak base this, strong acid this, weak acid this. So if it is a strong acid and weak base, we will get the graph like this and this line means this, like this, strong acid, weak base, strong acid, weak base. Or if it is weak acid, strong base, weak acid means like this and strong base. This is weak acid, this is strong base. Or if it is weak acid and weak base, this is weak acid, this is weak base. We get these two lines, weak acid versus weak base. But if by chance, suppose it contains the mixture of acids, in normal course of titration we can't study because we get only one endpoint pink color. It's not like if suppose I'm taking the mixture of acetic acid and HCl, then one pink color for HCl, one pink for acetic acid. No, I get only pink color only one time. But in this titration, we can successfully identify this is a graph of strong acid, then weak acid, and then whatever may be added, strong base or weak base. We can get the curves like this. And this intersection will give you the endpoint. So these titrations, conductometric titrations, are very useful, very good titration. Also in complexometric titration reaction, whenever we take the complexometric reactions, displacement reaction, precipitation titration, all such precipitation, what happens in the precipitation reaction? In precipitation reaction, PPT is formed. For example, AgCl, AgBr, AgI. We can't perform the complexometric titration in normal way because that PPT will interfere in the color. We cannot get the right accurate endpoint. But here, as we don't have to judge from the naked eyes, so we can, the endpoint is determined by the conductance measurement. That's why here it is very easy to determine the complexometric titration. Mixture of halides, AgCl halide, chloride, bromide, iodide, if they are mixed, we can easily get the three intersection points and we can find out the endpoint. Complexometric titration, stoichiometry of the complex compound, Jobs method is there, we can determine it from the break in the curve. So these are all the applications. There are several advantages of this conductometric titration over ordinary volumetric titrations. Conductometric titration, they are done to check the endpoint. They are also done to check the endpoint, but titration are carried out even with the color solution. But here volumetric titration, the color suitable indicator should be available. Here accurate results are obtained. Here results are not accurate because There should be just appearance of the pink color and what color you get, dark pink color. So these results are not accurate because one drop can make a difference. That's why in conductometric titration we have to be very much careful in adding NaOH. Here you add drop by drop. Here you have to take microburate and you have to add with precision, accuracy. Endpoint is determined graphically. Here endpoint is determined by the color change in the indicator. When there are mixture of acids, we can use conductometric titration, but volumetric they do not give the correct endpoint. When weak acid is present, then also it is successful. So conductometric titrations are considered to be good over the volumetric titration. But the fact is, these are very fast. Just take burette, pipette, add indicator and see the endpoint. But here you have to take lots of precaution, but the endpoint is more accurate. Now, this is Ostwald theory given for the weak electrolyte. Now, the theory of strong electrolyte. The number of theories has been put forward by different workers in order to explain the high conductance of strong electrolyte. In 1923, Debye-Hückel put forward the theory for strong electrolyte. And he has considered that strong electrolyte, they are completely dissociated even at moderate concentration. Now, there are three major factors on which this theory is based: relaxation effect, electrophoretic effect, and the frictional resistance of the medium. Relaxation effect. What is this relaxation effect? Electrolyte is dissociated in solution to give positive and a negative ion. Each ion is surrounded by an ionic atmosphere of oppositely charged ion. This ionic atmosphere is spherically symmetrical. When a current is passed through the solution, the center of the ionic atmosphere, it moves towards oppositely charged. Suppose this. So this negative is moving towards this positively charged electron. During this movement, it has to rebuild an ionic atmosphere because initially this was that ionic atmosphere, but when it is moving, so ionic atmosphere positively charged, it is moving towards this. So this ionic atmosphere is disturbed. It is not spherical. So it has to again build the new ionic atmosphere. At this time, the old ionic atmosphere dies out. These two processes, they do not take place simultaneously. There is some time lag, which we call it as a relaxation time, known as relaxation effect. So old ionic atmosphere pulls the moving ion backward and the motion is retarded. So known as relaxation or asymmetric effect. So this is the central negative ion surrounded by the positively charged ion which form the ionic atmosphere. This ionic atmosphere, it is symmetrically situated in absence of field. But when the field is applied, the negative ion moves towards anode. Positive ionic atmosphere towards cathode. So large number of positive ions are leaving behind it and these are pulling the ion behind. So now electrophoretic effect. In electrophoretic effect, application of EMF, the central ion moves in one direction and the oppositely charged ions which are present in the ionic atmosphere, they move in the opposite direction. It means that the central ion is moving against the flow, against the stream. So motion of the central ion is retarded. This is known as electrophoretic effect. The speed is retarded, the motion is retarded, known as electrophoretic effect. And what is the frictional resistance of the medium? Whenever an ion with its ionic atmosphere travels in the solution, then the medium of the solution offers the resistance. This force depends upon the viscosity of the medium and the dielectric constant. Initially, the force of attraction exerted by ionic atmosphere was uniform. It becomes greater now behind the ion that in front. As a result, the negative ion experiences a force which tends to drag it backward. This slows down the movement of the forward direction. This is asymmetry effect. Negative ion leaves the ionic atmosphere behind to die away, would build new ionic atmosphere and the symmetry would be corrected. If this process of building up and dying away building up and dying away of the old atmosphere. If it is instantaneous, there would be no cause, there will be no problem. But the formation of new ionic atmosphere does not take place at the same rate as that of old one decays, and the latter lags behind and take more time, known as relaxation time. So, central negative ion moving towards anode, it has to make its own ionic atmosphere. Both these above effects, they reduce the velocity of the ion and operated in the solution of strong electrolyte. So, Debye-Hückel put the equation as a Debye-Hückel-Onsager equation, which I have given you in the notes. It is the treatment which deals with the distribution of ions around a given ion and the net effect of these neighboring ions. Debye-Hückel derived an equation, Debye-Hückel-Onsager equation, for the strong electrolyte, which shows that how the potential energy of ion depends on the ionic strength of the solution. In case of strong electrolyte, the value of molar conductance at infinite dilution is much less than unity, which due to these effects. So the mathematical expression is given, which you don't have to derive, you have to write down directly the expression along with the notations used. Now in summary, what we have learned that in electrolysis, flow of current, it is accompanied with the actual transfer of migration of matter. You have studied in this unit that such transfer of matter leads to the decomposition of matter at the point where electricity enters or leaves the electrolyte. We have studied transport number also, Arrhenius theory also, Ostwald theory also, then Kohlrausch law also, Debye-Hückel theory also, and the advantages of conductometric titrations. So this is all about unit 5th. Now you have to practice more, and you have to practice for the numericals also. In the next talk, we will deal with the last unit, that is unit 6.